Okay, so it is time for the capstone. This talk is going to bring us to the very frontiers of our abilities to observe space weather around stars, which is the whole topic of this workshop. Right. Hopefully we'll get a sense of the state of the art that we're going to build upon. Our instructor for this lesson is a polyglot, but not in human languages, so she might be, but in the language of wavelengths. So she's observed in X-rays, she's observed in radio, she's observed everything in between. She is also the previous recipient of both the Jansky and the Hubble fellowships. And currently she is a tenured astronomer at the Space Telescope Science Institute, where she, among many leadership roles, is the head of the instruments division. Her enormous collection of observational research focuses on stellar activity and space weather, so it's a great privilege to hear about how we might be able to observe it for stars, or what we have tried, from Dr. Rachel Osten.
Thank you very much for that fabulous introduction. I hope the talk lives up to the expectations. So I'm gonna bring a lot of what we've talked about home, but home might not be where you think it is. So I'm going to talk about the frontiers of observing extrasolar space weather. As I was putting my slides together, I realized, this was sort of the intent, to focus on the observations, what we can observe, what kinds of questions we can answer. So it's physics light, I would say, but you've gotten a lot of physics already, and we can certainly take up that discussion during the rest of this workshop. I am also trying to cover, instead of just covering one star, I've got to cover all the stars in the galaxy, all of their wavelengths, radiation, magnetized winds, coronal mass ejections, and accelerated particles. So I'm necessarily going to have to gloss over some things. I'm going to try to give you a representative sense of what kind of measurements we can make and what we understand from those, but I'm not going to be able to go into any detail by any means. So just very quickly, a nice little way to encapsulate studying the sun versus other cool stars. People have already mentioned this a little bit. We've got one star. It's got exquisite spatial, spectral, temporal resolution, daily global monitoring, multi-wavelength context, an entire NASA division devoted to its study, specialized instruments and telescopes for its study. On the downside, it's one star at one point in its evolutionary sequence. We've already had that emphasized from other people. G stars are not representative of most stars in our galaxy, so we're not getting the context of what the typical star in our galaxy looks like. The specialized instruments is both a plus and a minus, because it means that it's much more difficult to do intercomparisons when you're talking about studying stars and studying the sun. And we have the question about how universal are the processes occurring in this atmosphere. That's something that Antigone raised, and that's something that's a sort of a recurring theme that I want to emphasize, that we need to be able to question our assumptions, because that's really where we can get to all of the meaty, interesting stuff that might be happening or not happening. In contrast, if you're looking at other cool stars, you've got millions, maybe billions of other stars to study. Low mass M dwarfs are the most common type of star, span a range of ages, rotation rates, and evolutionary histories. Some of the negatives are you can't actually spatially resolve them, so you need to be very creative in the observational tools that you use to both observe and then infer what you're seeing. Typically very sparse observations with little multi-wavelength context, showing some really wonderful Kepler light curves from this. This is a K star that you're seeing, and you can see the fast rotation is going up and down and causing that very short time scale variation. And then you've got a beat pattern with star spot emergence, lifetime dissolution, and you can just see that there's just a wealth of complexity in there from a star that we cannot spatially resolve. The other graph on the right is just showing time-resolved spectroscopy through the different phases of a flare. So that's another tool that we have, is looking at high-resolution spectroscopy, multi-wavelength observations. But oftentimes there's little multi-wavelength context. Similarly to the sun, there's different instruments and telescopes that are used to study stars compared to solar observations. And, small point, but you have to compete with the rest of the universe for observing time and funding. And this is just a very quick summary about just demonstrating the growth of interest in this field. One of the 3 areas that was called out in the recent decadal survey for astronomy and astrophysics was worlds and suns in context. And this idea of looking at space weather and the interaction and the interplay between the star and the planets, and having an understanding of what kind of impact on the near stellar environment the star is creating is going to be an important component of understanding those worlds and those suns in context. It's an ecosystem. So let me go to, very quickly, talking about measuring stellar magnetic fields. Julian did a very good job of describing the details, and I thought I would try to get to just a little bit of physicsy stuff. So thanks to this, to the European Southern Observatory for this nice graphic just demonstrating the Zeeman effect that Julian was showing, these wonderful Zeeman Doppler images that we can make of stars. So this is just showing how the quantum mechanical effects produce the spectral change as you change turn up the dial on the magnetic field, and then the impact of circular polarization. So that's one of our tools to look at an unresolved star, to be able to see that, yes, there is a strong magnetic field on the surface of the star. Doesn't get quite as much coverage, but there's another effect called the Hanley effect, using linear polarization. It gives you another constraint on magnetic fields. And I stole this from Julian, and he had to skip over it very briefly. So this is just to show you the confusogram, that we've got lots of different magnetic topologies when you do these Zeeman Doppler imaging reconstructions of what the surfaces of the magnetic field strengths at the surfaces of these stars look like. And trying to understand why you see this is one of the main topics for people like Julia. I want to go into other ways that you can measure stellar magnetic fields, not necessarily as precise. And each of these measurements has its own assumptions and biases built in. So there's I talked about some of those direct methods. There's indirect methods that we've talked about already, that stellar activity basically twiddles magnetic fields. And this is an example of that, where you can see the surface of the image of the sun in white light. There's a couple of sunspots which are kind of hard to see with this contrast. When you look at high energy radiation and when you look at radio microwave signatures, you're seeing the signature of those magnetic fields in either heated plasma or accelerated particles. So even if we can't resolve the surface of the star, if we see those emissions, that tells us that there's intense magnetic fields. There's other indirect methods. This is a plot from Kosuke Namakata-san, showing that if you do twiddle physics and say that the flare energy depends on duration, and you can work out that there's dependencies on the length scale of the the length scale of the emission or the magnetic field, and then you end up with this plot of flare energy versus flare duration. These are white light solar flares, and then these are sun-like stars as observed with the Kepler Space Telescope, either in very long, like 30-minute cadence or 1-minute cadence. And these lines tell you where you are in magnetic field space. So you can use this to get a sense of what the magnetic field strengths are in the flaring plasma. Another point to point out here that has been discussed a little bit is just looking at the very large range of flare energies. That's 8 orders of magnitude between the smallest flares that we can see on the sun and these very energetic events that we can see in stars. So that's one clue that's telling us that we really are seeing something very different when we look at these stellar flares. Another indirect method, radio observations, loosely constrained magnetic fields through incoherent and coherent emission mechanisms. This is an active region on the sun, showing some, you've got the magnetic field lines of force, and then these curves are isogauss layers. So those are layers of constant magnetic field, and what you would see if you observed at different frequencies, 5 gigahertz, 8 gigahertz, 11 gigahertz. So by tuning the wavelength region that you're observing, you're sensitive to different magnetic field strengths. This I threw in just because I think we should mention the rotation activity correlation. It's a sort of a very fundamental something that underrides a lot of what we're seeing when we talk about stars. Activity correlates with rotation. That is the fundamental. That is the fundamental thing. You've got saturated and unsaturated regimes. The sun would be somewhere around here, and then these would be saturated stars, unsaturated stars. In single main sequence stars, rotation is a function of stellar age due to the angular momentum loss from a magnetized wind, and that's what's responsible for producing this the stellar spin down. Important to remember that's for single main sequence stars. So now let me very briefly talk about stellar flares. We observe stellar flares across the electromagnetic spectrum. I like making tables like this where you can kind of put solar and stellar on the same plot, and there's a number of things to remember. When I say stellar, that's across different cool stars. We don't have all of these observations for even one single star, so it's a concatenation of a lot of different information. And the sun, by design, there is a check mark in each of these boxes. So there's different observational flare signatures. Flares are a multi-wavelength phenomena. They involve all layers of the stellar atmosphere. The graphic on the right just gives you this coronal loop and the magnetic reconnection process, which is accelerating particles that can either shoot up out of the atmosphere or downward into the atmosphere. Some of those particles become trapped and then emit radio waves as they are trapped. You've got non-thermal hard X-ray emission from precipitating particles at the foot points of this loop. That energy gets deposited lower in the atmosphere and heats that plasma to coronal temperatures, which you observe later on in the event as coronal emission and chromospheric emission. And this is a very kind of idealized scenario, but provides the context for what we think we're seeing when we're looking at the multi-wavelength context. And based on some of those signatures, we infer that we're seeing the same physical processes as in solar flares, even though there are marked differences. So the plot on the left is from Ashwaubenon, 2008. There is a long heritage of making temperature emission measure plots for solar and stellar flares. This is a collection of different types of solar flares, different types of stellar flares, a very heterogeneous set. What is remarkable is that they have the same power law in this temperature versus emission measure. The stellar flares, by and large, are significantly hotter, and they have significantly higher volume emission measures. And that could be because either they're denser, the coronae are denser, or the volumes are larger. When we look at individual stellar flares, we see evidence for that basic process that I was describing before. We call that the Newport effect, where you see a relationship, an observational relationship between signatures of accelerated particles and signatures of the heated plasma. And this is for an example on an active binary system where there was a very impulsive radio flare right before an X-ray flare, which matches that expectation. However, there's complexity in what's seen. I don't want to spend a huge amount of time on this, but stars don't read APJ. They don't necessarily know what they're supposed to do. And we're finding evidence that there's a variety of different kinds of multi-wavelength correlations This is one example from a recent paper on the planet hosting M-dwarf AU-MIC, where we see this Newport effect type flares, but then there are things that Isaiah Tristan called quasi-Newport flares, where, yeah, there's a UV flare and an X-ray flare, but it's not really what you would expect for a Newport. And then there are situations where you see one response and not the other. And so trying to understand what gives rise to those observational signatures is an important next step. All right, so now I'm going to go on to observational signatures of magnetized winds. I think this is like the third or fourth time we've seen this particular image, so I don't need to explain it. Thinking about winds, it's more like space climate, I thought, than space weather, right? Space weather changes on a day-to-day timescale. Climate is something that's broader, changes more slowly. Your space climate will be different if you're in Hawaii compared to California, compared to Maryland. Stellar astronomers need to be creative when we get to looking for signatures of winds. We've already heard a little bit about UV Lyman alpha. I'm going to talk also about radio bremsstrahlung and X-ray scattering, which we've also heard about. So fortunately, I can speed through this. Lyman alpha astrospheric constraints on cool stellar winds. One thing I want to make sure that you take away from this is that we have very few direct measures of mass loss, of stellar wind mass loss. This Lyman alpha astrospheric absorption is currently the main way to produce constraints on steady winds in the cool half of the main sequence. It is an indirect method. You are not detecting the wind, you're detecting the effect that the wind has on the larger scale astrosphere. You can only do this with high resolution spectroscopy from space, basically the STIS spectrograph on Hubble. You're detecting the bow shock that's created when the wind interacts with the local ISM. That's what I already said. Non-detections do not really provide upper limits to stellar mass loss. So this is an example of evidence for a weak wind from the young sun, presented by Brian Wood in 2014. This is the blueward wing of Lyman alpha, and these various curves, which might be kind of hard to see, are based on astrospheric models for what the mass loss rate would be from a stellar wind, given all of the scalings that we see in our heliosphere apply. And then if you do that, you can see that there's like a little extra blueward absorption here between Lyman alpha and deuterium Lyman alpha, and by fitting that, you get a constraint on the mass loss rate. These are some newer results from Brian Wood showing his mass loss per unit surface area as a function of surface X-ray flux for different types of stars, M dwarfs, GK dwarfs, subgiants, and then slingshot prominence winds come from a different reference. So I'm not going to talk about that. But his main takeaway points here that coronal activity and spectral type alone do not determine wind properties. And we have a number of stars that have very low measures of mass loss rate, lower than what you infer from the sun. There's an inconsistency between CME-dominated winds from extrapolating from solar flares and CME connections. And I don't have time to go into that in detail, but I can talk about it later. We can discuss that later in the workshop. Radio bremsstrahlung signatures of low-mass stellar winds. This is the point that Julian showed in his slide on limits on mass loss from Proxima, from charge exchange emission. Here is EV-LAC, which has a constraint from the astrospheric method. This plot is several years old now, so it doesn't have the latest results from Brian Wood. And this is just to say that we can detect or constrain radio emission from an ionized stellar wind if we have sensitive surveys of nearby planet-hosting M dwarfs. And this technique, there are devils in the details, but you can actually put an upper limit on the mass loss rate from a non-detection. And let's see. This is just to connect with what Julian presented in his stellar wind of Proxima Centauri. So I'm not going to go into this in detail, but that gets me my gold star for reusing slides. So let me then go into observational techniques for transient stellar mass loss. Again, the kind of table that I like to prepare with observational signature. And the sun, there's a check mark in almost all of these. And then in stars, check marks indicate where this has been attempted or where it's just not even feasible. So again, I'm not going to be able to go through all of these in detail. I'm going to pick a couple with the time that I have and talk about those. So type 2 radio bursts we heard about in the last slide. This has a lot of potential for detecting coronal mass ejections on stars because it comes from the CME itself. What you're seeing when you see this fantastic drifting structures that are drifting in frequency and time is as the shock is propagating through the atmosphere of the star, it is producing Langmuir waves that gets converted to plasma radiation. That's tracing the electron density. And as you go upward out of the atmosphere is getting more rarefied. So you see that characteristic drop. It's got a predictable signal. We can predict that based on what we understand about stellar magnetic fields. And so this is, and it gives you constraints on the exciter speed, the scale height of the star. So there holds a lot of potential, but it's currently unfilled. So a graduate student of mine and I tried to detect type 2 radio bursts using low frequency, very large array observations. We targeted one very high flaring rate star, and our observations were posited on this flare CME connection that if you had a high rate of flaring coupled with a high rate of CMEs, you should be able to detect many of these, even if you had very restrictive assumptions about just the most energetic events. And these are some of the optical flares observed during one particular scan. This is the dynamic spectrum in Stokes I and Stokes V. This is just the real and imaginary components of the data. The situation is we didn't see anything. We did see one burst that was not consistent with what we would expect for the properties of a stellar CME to look like. So either CMEs with flares are rare, or the conditions to create shocks are not present at the observing frequencies and distances that we're probing. Let me move on to some other signatures of eruptive events, looking at dimming and outflow signatures. This is a graphic from a paper by James Mason showing a couple different kinds of dimming signatures where mass loss dimming happens, where you see a decrease in emission due to the evacuation of material, and then absorption dimming shows up as a temporary increase in absorption as absorbing material moves across the line of sight where the flaring material is occurring. Absorption dimming is a promising signature for stellar CMEs. This is an example from a few years ago interpreting the time dependence of variations of the column density of hydrogen that you infer when you do X-ray measurements. You need to account for the fact that there's some usually interstellar hydrogen in between you and the star, but if you have some circumstellar extra absorption, you can see that as a temporal, you can see that in the temporal domain. And this was interpreted as originating from a constant velocity self-similar expansion of a CME front. Mass loss dimming is another promising signature of stellar CMEs. This is from, where is Astrid? There she is. So this is the idea being that you're seeing dimming detections associated with flares on cool stars. 2 minutes. This is indicative of stellar CMEs benchmarked by Sun as a Star EUV measurements. that these shaded regions show the regions of the light curves of these active stars where dimming signatures are inferred based on comparison to the pre-flare and post-flare measurements, and you seeing a decrease in that. Let me go very quickly through the next couple of slides to talk about dimming and high velocity outflows in chromospheric lines during flares, where you can look at the velocity of the emission, and if it is greater than the escape speed of the star, you have a compelling claim to have seen a coronal mass ejection. That happens sometimes. It doesn't happen all the time. This is an example from X-ray observations where they inferred the existence of flows during several flaring events, but these are traveling at less than the escape velocity. So in my less than 2 minutes, let me talk about particle acceleration. We've already seen this graphic in a couple previous slides, so I'm not going to go into a huge amount of detail, but just to it's already been emphasized that there's particles can be accelerated in the shock fronts associated with CMEs, as well as with flares. And so let me talk about particle acceleration in flares, because that's where we have a hope of some measurement constraints from stars. The main method that solar physicists use is non-thermal hard X-ray emission from non-thermal Bremsstrahlung. We can't do that with stellar flares. Just this plot should hopefully show you why. There's 5 orders of magnitude here between the thermal energy and the non-thermal energy. Stellar flares are much hotter. I showed you that before. And so when you're looking in the hard X-ray range, you're predominantly seeing thermal plasma, very hot thermal plasma, but thermal plasma. Gyrosynchrotron emission. We also have a hope of getting some constraint on the index, on the properties of accelerated particles. In particular, you need to make sure that you're looking at optically thin emission. That's this side of this schematic diagram of flux versus frequency. The spectral index of the emission that you're seeing, you can trace directly to the index of the accelerated particles, the distribution of the power laws. If you have wide enough bandwidths, you can see impacts of the cutoffs, the lowest energies and the highest energies that you can see. Coherent emission, just very briefly, if you've got plasma emission, this is another example of some of these type 3 bursts, reverse slope bursts that are traveling back down into the stellar atmosphere. We have some constraints on this from stellar observations. But we don't have quite the same kind of span of wavelength coverage here. And then cyclotron maser emission, where the observing frequency is proportional to the magnetic field strength. All right, and then constraining particle acceleration in stellar flares. This is my second or third from last slide. So the blue optical flare spectral energy distribution that we see often has the shape of a black body. It's been known for a while that if you try to model this white light continuum enhancement, you need to have a beam of accelerated electrons. There are work that's been done in the sun showed that if you take a solar-like electron beam and put it in an M-dwarf atmosphere, you don't get an M-dwarf flare. If you want to get an M-dwarf flare, you've got to turn the knob up by a lot. This is a paper revisiting the Great Flare of AD Leo, which is often used for astrobiology papers. Here you can reproduce the spectral signature, but with a beam flux that's 2 orders of magnitude larger than the largest thing we've seen in solar flares. So that's a hint of a disconnect in particle acceleration between solar and stellar flares. Just very briefly, we also have hints of a disconnect when we're looking at radio emission. This paper from Smith et al. Suggests that there's more energy in non-thermal particles in these radio flares seen on M-dwarfs than is seen in the X-ray emission. And you can see that over here with the scaling between solar flares and X-ray radio comparisons for a stellar flare. So I know I'm out of time, and I'll just conclude. I won't actually read all of this, but I'll end with an anecdote that I was going to start with at the beginning and then I forgot. When I was defending my dissertation many, many decades ago. The department that I was in had been a planetary atmospheric science, Earth atmospheric science, and astrophysics. And one of my friends, who is an atmospheric scientist, came and listened to me give my talk on multi-wavelength observations of stellar flares. And at the end, I said, you know, did you understand? Did you get anything out of my talk? Because it was a lot of specialized, you know, language. And he said, I learned that there's a difference between solar and stellar. So, thank you.